Hello everyone. Today I will start a next lecture on the characterization of protein adsorption. In the last lecture we discussed the basics of proteins, structure of protein, primary structure, secondary structure, tertiary structure and quaternary structure. Then we discussed what are different functions of the protein. Then we talked about what are different non-covalent interactions apart from the covalent or the peptide linkage. So, we discussed the hydrophobic interaction, hydrogen bonds, electrostatic interaction and dipolar interactions. Also we discussed what is the protein stability, the Gibbs free energy of the protein folding, what are different factors which affect the protein stability like the pH, temperature, some ionic strength including the adsorption. So, today we will discuss when a protein comes into contact with the surface, so there will be the protein adsorption. Now, how to characterize the adsorption? So, for that we will first discuss how to determine the amount of adsorbed protein on the surface, or you can say that is the surface excess, and apart from that we will also see how we can analyze or understand what is the property of the adsorbed protein, what are the secondary structures of the adsorbed protein, how can we analyze the thickness of the adsorbed layer, whether it is a monolayer or multilayer, how can we know the what is the soft film or rigid film, or you can say what is the viscoelasticity of the adsorbed layer. So, first we will quickly see, as I discussed in the last class, we are having a surface, you may say this biomaterial implant, it is coming in contact with the body fluid. So, body fluid mainly consists of three components: water molecules, biomacromolecules like proteins, then cells. So, depending on their diffusivity, first water molecule will come to the surface, followed by the protein, then cell will come to the surface. So, in case of protein surface interactions, there will be adsorption of the protein due to various interaction between the surface and the protein. Now, depending on the surface property, as we discussed in the last class, if surface is having charge group, so there will be the electrostatic interactions. If surface is hydrophobic, there will be the hydrophobic interaction. If surface is having some hydrogen bond forming groups, there will be formation of hydrogen bond between protein and surface. So, that interaction between the surface and protein may lead to the making and breaking of different intermolecular interactions, and those interactions may lead to the unfolding or denaturation of that particular protein. So, as we know, the function of protein is totally dependent on its native or folded structure. So, if the protein is unfolded or even denatured, so its functions will be lost. So, if there is a protein adsorption, so we have to first analyze what is the amount of adsorbed protein, or also it is called surface excess, how much quantity of protein which is present on the surface, and further important is whatever protein or adsorbed layer is present, what are its properties, in the terms of secondary structure, whether it is close to native state or whether it is unfolded or it is denatured or aggregated, what is the thickness of the adsorbed layer. So, you can say it is whether it is a multilayer adsorption or monolayer adsorption, and what is the viscoelastic property of the adsorbed layer. So, these things are very important to analyze the adsorption behavior of protein, particularly on a surface. So, if you want to analyze the adsorbed protein, so there are different methods including the labeling method, colorimetric method and instruments based method. So, labeling method means we are having a protein molecule, we can label a particular amino acid with some radioactive isotopes. So, if you can target or if you can track that particular amino acid, you should be able to see what is the conformation of the particular protein or what is the concentration of the particular protein depending on the intensity of that radio labeled compound. In the colorimetric method, we see what is the concentration of the protein. So, that we can do in two methods, one is in the solution, other is on the surface. Solution means we call solution depletion, means protein was there in the bulk solution, when it is adsorbing on the surface there should be decrease in its concentration. So, we call the depletion, but typically what happen in case of protein adsorption, the adsorbed mass on the surface is very less, it is in the range of nanogram per centimeter square to milligram per centimeter square. So, in that case the change in the bulk concentration is not very significant. So, typically it is difficult to analyze through the solution depletion method. The other option is whatever protein is there on the surface, if we can desorb in less volume. So, we can get some concentrated protein and then we can analyze using the colorimetric method. And third method is we have various high end equipment which can directly measure or characterize the various property of the surface, and whenever there is adsorption there will be change in the surface property. So, these instruments relate the change in the surface property with the adsorbed mass. So, in the labeling method we can go for the radioisotope labeling, then fluorescent labeling, and we can also go for the staining or dye. So, if you are going with the radioisotope labeling, so it has very high signal to noise ratio, and particularly you can analyze up to the nanogram of the protein, very small amount of the protein. But if you are using the radioisotope, means we are susceptible to the gamma emissions, and also the disposal of the radioactive materials or radioactive substance requires a sophisticated facility, and that is also a challenge. So, for radioisotope we can have I-125, I-131 or P-32. So, these are the compound we can particularly attach to a amino acid, and depending on the concentration of the particular amino acid or particular protein, we will have the bearing intensity of these radioisotopes. So, depending on intensity we can analyze what is the adsorbed protein. Next method is the fluorescent labeling. So, rather than you are adding some isotope, we are adding some fluorescent molecule like FITC, or we are having some Alexa fluor or some Alexa dyes. So, these molecules bind to the primary sequence of a protein, then depending on the fluorescent intensity we analyze what is the amount of adsorbed protein. If there are more number of protein molecule, the fluorescent intensity will be higher. So, merit of this is it is a safe chemistry as compared to the radioisotope labeling, and no additional reagent is required. We can directly measure the fluorescent intensity to analyze the adsorption. Demerit is it is having the low signal, and the fluorescent, if you are doing the tagging, adding a fluorescent molecule to the protein, it may interfere with the adsorption process, because this particular fluorescence molecule will have also certain chemistry which can interfere with either intramolecular interaction or the intermolecular interactions or the protein surface interaction. The third method is we are going with the simple dye like silver staining or some other staining. So, its merit is again it is having the safe chemistry, but if you are doing some staining it is non-specific. So, it can bind, we cannot say it is binding to which particular protein or which particular amino acids. So, these are the three labeling method. We can label with radioisotope, the fluorescent and the some dye or staining. So, when we go for these first two methods, so one more issue with these two methods is if you are adding some extra molecule in that protein, then behavior of that native protein and the labeled protein varies. So, in that case whatever adsorption behavior we are analyzing, that may not actually reflect the native protein or the actual protein system. So, ultimately we can say this labeling is interferes. This labeling interferes with protein, you can say protein interaction, also it interfere with the protein surface interaction. So, this is the major challenge or major drawback with this system. If you are labeling a protein, we are not very sure whether it is behaving like a native protein or not. So, next method is the colorimetric method. So, as I told, colorimetric we can go with either solution depletion method or we can go with the desorption from the surface. So, if you can desorb the adsorb amount in a small volume, so we can have a higher concentration of the protein suitable for the analysis, because in case of solution depletion method there is no significant change in the bulk concentration. So, that is why it becomes very difficult to analyze the solution depletion method, but in certain cases like when you are dealing with the protein aggregation, in case of protein aggregation almost all the protein in the bulk will be depleted and converted to the aggregates. In that case the bulk concentration goes to the 0. So, for such cases of course we can analyze the solution depletion method, but typically when we go for the surface protein interaction or the protein adsorption, in that case the change in the bulk concentration is very less. So, we desorb the adsorbed protein from the surface, then we go for the analysis. So, in the colorimetric method we are adding certain reagents, that reagent will form a complex or reacts with the protein or its complexes, and after this interaction there should be some measurable change in the color, and that color we analyze in the visible range 380 to 780 nanometer. and to analyze the color we use the simple spectrophotometer and we record the optical density. So, if you want to use the colorimetric method, then we will have some unknown quantity, we will have some value of optical density, but how to calculate the concentration. So, for that we need to prepare a standard curve. So, standard curve, so here we are having the known concentration of the protein, we are following the same procedure, we are measuring its optical density. So, this is like a concentration and this is let us say optical density having different experimental points. So, this is a standard curve and from this standard curve we can analyze for any unknown samples. So, there are different methods are available. I have listed a few, let us say this Folin reagent or the BCA method and the Bradford methods. So, I will quickly discuss one by one. So, in case of Lowry method, it includes the phosphotungstic acid and phosphomolybdic acid. So, these are the components of that Folin reagent, and here also we are using the copper ions. So, copper ion in alkaline solution it complexes with the peptide bonds or NH group of the proteins and it reduces the copper 2 plus to copper plus. Now, once the copper plus is present, now this copper plus reacts with the that Folin reagent and when it bind to the reagent we got a change in the color and we observe a blue color, and the formation of this purple blue color is dependent on the concentration of reduced copper ion and the concentration of reduced copper ion is dependent on the concentration of the protein. So, this is indirectly the protein molecule or protein concentration is reducing copper 2 plus to the copper plus and the copper plus is binding to that Folin reagent and giving a blue purple color. So, the intensity of color will depend on the concentration of the copper ion or you can say indirectly to the concentration of the protein. So, this is you can say the NH group of the protein will form some complex with the copper 2 plus ion, then the copper 2 plus will reduce to the copper ion and the copper ion will reagent to the Folin reagent, it will give the blue color. So, and then we can analyze its absorbance in the range of 650 to 700 nanometer. So, advantage of this method is its high sensitivity. So, we can analyze the small amount of the protein. Also, it does not Folin reagent does not affect the turbidity of the solution, and as this is simple method because we are simply using some reagent and measuring the optical density or the absorbance. The disadvantage is as it depends on the aromatic amino acid. So, the concentration sometime may not be equal to the or you can say the intensity of color may not be equal to the concentration of protein because it depends on the particular amino acid residues. So, next method is Bradford assay. So, here we are using Comasy brilliant dye G250. So, what we are measuring after adding the dye we will see its shift in the absorbance. So, this dye binds to the aromatic and basic amino acids present in the protein which shift the maximum absorbance from 465 brown color to the 595 blue color. So, here directly the dye is binding to the, or you can say protein is binding to the dye molecule, and then there is a change in the absorbance from 465 to 595 nanometer, and as I told, this peak shift is shift of absorbance or intensity is directly proportional to the amount of the protein. So, if you can measure what is the change in the intensity or what is the peak shift from 465 to 595, then we can calculate what was the concentration of that particular protein in the solution. So, merits include, it is applicable for protein which contain low or no aromatic amino acid, because it also binds to the basic amino acids, and its sensitivity lies in the range of 1 to 20 microgram of proteins, and as it is directly interacting with the protein molecules. So, it has some demerits, like its linearity range is up to 2000 micrograms. So, it requires the dilution of the samples. Also, the results may vary if the standard protein does not react the way a test protein does. So, if you want to measure a particular protein A, so we have to prepare the standard curve also for the same protein A. The next method is the BCA assay. So, it works in the similar principle as the Lowry method, where the peptide bond reduces copper 2 plus to copper plus, and which is equal to the amount of protein present in the solution. Now, this copper plus ion, it binds, or you can see it chelates with the BCA molecules, and which results in the formation of purple color. And this complexation is favored at 60 degrees centigrade. So, typically we incubate at 60 degrees centigrade for let us say 1 hour, or you can say also if you are incubating 37 degrees centigrade, we have to incubate for 2 hours. So, after the incubation we get the purple color, then we can measure the absorbance at 562 nanometer to estimate the protein concentration, and its linearity range vary between 0.02 to 2000 microgram per ml. So, it has certain merits. This process is not affected by the detergent in the solution. The detergent, typically what happens when we go for the desorption of the protein, we use some detergent like SDS. So, this method is not affected by the detergent in the solution, and whatever color is formed, it is highly stable, and of course, as we saw, its linearity range is 0.02 to 2000 microgram per ml. It has few demerits also, that long incubation time, 1 hour, 2 hour required for the development of the colors, and presence of copper chelating agent. If you are having some copper chelating agent, so it can interfere with the concentration of the reduced copper ion. So, that may interfere or affect the results. So, these are the 3 colorimetric methods: Lowry method, Bradford method, and BCA method. Now, next we will go to the instrument based method. So, we go for various instrumentation. I will discuss a few here. The first one is the surface plasmon resonance, then quartz crystal microvalence, ellipsometry, atomic force microscopy, small angle X-ray scattering, Fourier transform, infrared spectroscopy. So, main advantage of these instrument based method or technique is they are label free, they allow the in situ analysis and in the real time. So, we can get the kinetic data of the adsorption, we can go for the level free analysis, as well as we can see directly the in situ when protein adsorption is taking place at the surface, at the same time we can analyze also. So, for these methods, whenever there is a protein adsorption, there is going to change in the surface property. So, that surface property may be its refractive index, it may be its absorbance, it may have some other optical properties, or even it may have some change in the frequency. So, whatever change in the surface property is coming, it is coming because of the adsorption, and we can relate this change in the surface property with the amount of adsorbed protein. So, the first method is the surface Plasmon resonance. So, this is a optical technique which measure the change in the surface dielectric property, and it is used for the real time and in situ analysis. So, the surface plasma occurs when the plane of polarized light strike the thin metal surface. So, this is the polarized light source is going, this is your metal film, and here is your liquid or air. You can say here is a protein solution. So, this top layer there is going to be some adsorption or interaction at here. So, we are having this when this polarized light source strike the thin metal surface, then we will observe the surface plasmon. So, we are having the two waves, one is the KEV and other is the KSP. So, when the plane polarized light is focused on the surface of a prism. So, typically we have a prism surface SPR and that is coated with a gold. Its angle is let us say some theta angle, then KEV evanescent wave penetrate the interface into less tension medium to a distance, that distance will be equal to the one wavelength. So, it penetrates the interface into less dense medium to a distance of one wavelength. So, KEV or wave vector of the evanescent field is directly proportional to the wavelength 1 upon lambda is equal to here c is the speed of the light and omega is the frequency of the incident light, and Ng is the refractive index of the dense medium, or you can say that of the prism, and theta is the angle of incident, the theta is the angle of incident. So, one wave is the evanescent wave KEV and other wave is the on the top is the KSP. So, that is the wave vector of the surface plasma KSP, that is equal to the frequency upon speed of the light into here we have to take the consideration of the dielectric constant of the metal surface and the refractive index of the sample. So, for the top layer we have to consider the refractive index of the sample. So, if it is penetrating, then it couples the free oscillation of the surface wave vector, or you can say the KSP equal to the KEV at a certain angle of the theta, and that theta is known as the theta SPR. When we are passing this polarized light, the value of theta, it should be in such a way that it matches with the theta SPR, and that theta SPR should be always greater than the critical theta. The critical theta value we calculate sin inverse reflective index of the low density divided by the reflective index of the high density. So, high density we consider the prism and low density we consider that particular protein. So, we know what is the refractive index of the individual. So, we can calculate what will be the value of critical theta, and the theta SPR should be less than that of the critical theta value. Again this resonance effect is also depends on the surrounding environment. It may be the buffer you are taking, what is the temperature, what is the ionic strength, which is ultimately going to affect the property of the adsorbed layer. And whenever there is a adsorption, we are going to observe the change in the SPR angle or the reflectivity loss. So, because of the change in the SPR angle, we can say there is some change in the surface property. Like here, this is the angle and this is the reflectivity. We are seeing there is change in the SPR angle. That same we can replot in terms of SPR angle versus time, and then you can just see this value is increasing and reaching to the plateau during the protein adsorption, and once the adsorption process has reached to the plateau, we are washing with the buffer to remove the loosely adsorbed or unadsorbed protein. Then you can see there is a slight decrease in the plateau. So, depending on the, or you can see the change in the SPR angle can be converted to analyze the kinetics as well as the, it can be analyzed to extend the protein adsorption as well as the kinetics of the adsorption. So, if you perform the experiment, initially we pass the buffer. So, this is we pass the buffer. So, we call this is a baseline. Then from here we started the passing the protein solution, then there is change in the SPR angle, or you can say increase in the SPR angle, and there is a plateau formation, and from this we can calculate what is the adsorbed amount, as so we can calculate what is the kinetics of adsorption. So, if you just see this curve, it looks like a simple first order kinetics. So, you fit this with a single exponential function RT is equal to R infinite minus R 0 under bracket 1 minus e to the power minus k into t plus R naught, because R naught is not 0, it may have certain value, and here the k is the adsorption constant. Now, if you see the protein adsorption process, so it is equilibrium between the adsorption and desorption. Here the k includes both Ka adsorption and Kd desorption. So, if you want to calculate only the Kd, if you fit, or you can, if you analyze this desorption process, so here the value of K will be Kd, and here the value of K is equal to Ka plus Kd. So, if you can calculate K from here and Kd from here, this section, then we can calculate the value of Ka. So, in this way we analyze the adsorption kinetics as well as the amount of adsorbed proteins. Next method is the quartz crystal microvalence. Quartz crystal microvalence is having a crystal which vibrates at its resonance frequency, and whenever there is a change in the mass or something extra is coming on the crystal, it leads to the decrease in its frequency, and the decrease in the frequency is related with the adsorbed mass by Sauer-Brey equation. So, it says delta f or change in the frequency is directly proportional to the delta m, also it is related with the property of the crystal. So, the quartz crystal is a piezoelectric material, it means if you apply the mechanical state it can be converted to some electrical signal and vice versa. So, f naught is its resonance frequency, A is its area, rho q its density and mu q is its shear modulus. So, as we know these things are the constant, its resonance frequency is constant, area of the crystal is constant, its density and the shear modulus is constant. So, we can calculate this constant value and it can be written like delta m is directly proportional to delta f times c, c is the constant, and if you calculate this value for a from the given data it comes out to be 17.7 nanogram per hertz per centimeter square. Also we can play with the overtone. So, whatever its resonance frequency is there, we can go with the third overtone, fifth overtone, seventh overtone, ninth overtone. Then whatever overtone is there, we have to normalize with divide by that overtone to calculate the adsorbed mass or delta m. So, this is a typical setup of the quartz crystal microvalence. So, this is, if you see this yellow color, this is a quartz crystal. Here we are having some port. So, in one port you can have the inlet, here it is showing what do you want to do, you want to pass the this direction or this direction, you can tune from here, and here we are passing either buffer, also we can pass the protein solution, again we can pass the buffer and so on and so forth. So, this is a chamber which is having a crystal, over the chamber we are passing the solution, and if you are passing the solution we can analyze the protein adsorption in the static mode, or you can say equilibrium, or in the dynamic mode in the flow conditions. So, we are monitoring the frequency, so there will be change in the frequency due to adsorption. Also at the same time it monitors the dissipation factor. The quartz crystal microvalence also monitors the dissipation factor. So, this is a typical result we get. So, the green line indicates the frequency is decreasing. So, what we are doing, we are passing the buffer here, then there is a we are passing the protein, it is reaching to the plateau, then we are doing washing here, then again we are passing the next higher concentration of the protein, higher concentration of the protein. So, there is an increase in the adsorbed mass, finally it has reached to the plateau, whatever you pass the surface is totally saturated, and corresponding to the decrease in the delta f or a frequency, there is an increase in the d value, dissipation. So, it indicates that the energy dissipated is increasing because of the presence of the adsorbed layer. So, we monitor both frequency which is used to analyze the adsorbed mass, while the dissipation factor or D is analyzed to monitor the viscoelastic properties of the adsorbed layer. So, as I told, first you have to pass the buffer solution, then if you want to use the surface modified crystal, then that also is possible. Then you pass the protein solution, then again you pass the buffer solution to remove the unadsorbed one. Then if you want to pass, let us say here you pass the protein A, here you can pass the protein B, you can pass the protein C, or you can also pass the same protein, but you can increase the concentration. So, this can also be used for the sequential analysis or competitive analysis, or effect of the concentration of the proteins. So, let us say in one experiment we observe the delta F value is 0.1 Hz. Now, if you want to calculate what will be the delta M, so delta M is equal to C into delta F, and value of the C is 17.7 into 0.1, it is coming to be 0.177 nanogram per centimeter square. So, we can say this is close to 1.77, this is close to the 2 nanogram per centimeter. This is the typical sensitivity of the quartz crystal microvalence, it measure up to the 2 nanogram per centimeter square or even lesser than that. So, as I told, it directly or parallelly monitor the dissipation factor. So, dissipation factor is defined as the ratio of energy dissipated divided by the ratio of energy stored, and that ratio indicates whether it is a rigid layer or the soft layer. So, in case of rigid layer, you can say the decay of the oscillation is different as compared to the soft layer. So, decay of oscillation of the rigid and soft surface decides the value of the dissipation factor. So, we can say this is a rigid layer and this is a soft layer. So, the change in the frequency, or you can say the decay of oscillations will be different. So, if you directly measuring the dampening effect or the D value, then we can also understand what is the viscoelastic properties, or we can say the adsorbed layer, whether it is a soft layer or whether it is a rigid layer. So, another way to analyze is if you simply plot the ratio of delta D upon delta F. The delta D says increase in the or change in the dissipation factor, delta F says change in the adsorbed mass. So, if its slope value is higher, it means surface is having more dissipation, it means it is a soft layer, and if it is a rigid layer, it is going to have the lower slope. So, here if you just see, so you can say this one is the soft layer and the lower one is the rigid layer. So, if you simply plot delta D and delta F, so based on the slope we can comment on the viscoelastic property of the adsorbed layer. Next method is the ellipsometry. Again it is a optical technique which characterize the light reflection or the transmission, or you can say the dielectric property of the adsorbed layer or the thin film. So, here we are passing a polarized light. So, it may have the reflection or transmission. So, that polarized light becomes elliptical. So, this is a light source, let us say this is a laser, it is by going through the polarizer, then coming to the surface, then again it is reflected through an analyzer, then going to the detector. So, during this process we monitor amplitude ratio as well as the phase difference between the parallel and perpendicular light waves. So, whatever light waves is coming, we can draw what is its value in the parallel and the perpendicular directions. Then from these values, amplitude ratio and the phase difference, we convert what is the layer thickness and what is the refractive index, and if you know what is the layer thickness, what is the refractive index, we calculate the adsorbed amount by simply df layer thickness times what is the reflective index of the film, what was the reflective index of the liquid, and what is the ratio, how the reflective index changes with the concentration. So, for this we have to plot C versus N. So, this is the slope, this is simply the slope value, or you can also say this, if you know the what is the thickness, we can simply multiply with the density of the layer, we can calculate the adsorbed mass. So, using ellipsometry, the thickness resolution is 0.01 nanometer or better. So, using ellipsometry we can measure the thickness as well as the refractive index, and that can be converted to understand the behavior of the adsorbed protein, or you can say the amount of adsorbed proteins. And also depending on the thickness, as we know what is the particular size of a particular protein, then depending on thickness we can also comment whether this is a monolayer or multilayer adsorption. So, these are the few instrument based method to analyze the amount of adsorbed protein, the SPR, ellipsometry and QCM. Now, we will discuss how to analyze the secondary structure of the protein. So, here we will discuss two methods, one is the Fourier transform infrared spectroscopy FTIR and circular dichroism CD. So, in case of FTIR, as the name suggests, we are passing the IR light, and the IR light is the Fourier transform to get the absorbance signal. So, this is the basic principle of the FTIR. So, we play with the three regions, near IR regions, mid IR regions and the far IR regions. So, wavelength for the near IR is 1 to 2.5 micrometer, for the mid IR 2.5 to 25 or even we go up to 50 micrometer, and far IR the 50 to 1000 micrometer. So, typically when we see the FTIR, especially for the protein or biomacromolecule, we go in the range of mid IR, you can say the wave number in the range of 400 to 4000 centimeter inverse, or wavelength 2.5 to 25 micrometer. So, we typically for the protein in this particular mid IR region, we have the amide 1 region 1600 to 1700, then amide 2 region 1470 to 1570, amide 3 region 1250 to 1350, and amide A region 3300 to 3500 centimeter inverse. So, these amide 1, amide 2, amide 3 and amide A represent or comes from the different functional group of a particular protein, like amide 1 reflect the CO stretching, amide 2 reflects the NH bending, amide A reflects the NH stretching, and amide 3 represent the CN. So, depending on the this is CN, this is the NH stretching, amide 1 is the CO stretching and amide 2 is the NH bending. So, depending on the different functional groups, we can analyze the particular protein in different regions. Mostly we analyze in the range of amide 1. So, this is a FTIR spectra of your sample. So, what you have to do? We have to deconvolute, and after this you are getting different peaks. So, for alpha helix, if the peak lies in the range of 1648 to 1657, we call it a alpha helix peak before beta sheet, if it is at 1623 to 1641 or 1687 to 1695, and for the random coil we go from the 1642 to 1648, and for beta turn. So, here 1662 to 1686. So, we start with beta sheet, random coil, alpha helix, beta turn, again beta sheet. So, if you decannulate, so we will get the peak area of different peak positions. Then depending on the relative peak area, we analyze what is the percentage of alpha helix, percentage of beta sheet, percentage of random coil and percentage of beta turn. So, here if you are using the FTIR, there are two key challenges. First, the absorbance or the peak position of water molecule H2O also lies in the same range. So, we typically replaces H2O with the D2O. So, if we are replacing H2O with D2O, also we have to do the pH correction. So, typically the PD is equal to the pH plus constant. So, the value of C varies between 0.4 to 0.45. And another correction we have to do is the, because as it is coming amide 1 is the C double bond O. So, we have to do the CO2 correction. So, we go for the moisture correction as well as the CO2 correction in the FTIR analysis. Another method is we can go with the circular dichorism. So, this is the most sensitive technique. Here we can analyze directly in the aqueous solution. It involves the circularly polarized light and the unequal adsorption of left and right component of the polarized light comes because of the chiral molecules of, or you can say the secondary structure of the protein. And here we use the UV lights. So, far UV and near UV. So, far UV, this is less than 250 nanometer, it is sensitive for the protein structure. So, typically for protein secondary structure we work in the far UV region. Also near UV, the wavelength higher than 250 nanometer, and it reflects the contribution of aromatic side chains and disulfide bonds. So, here we calculate the ellipticity, and this is related with the left and right adsorption of the circular polarized light 2.303 upon 4 A of the left, A of the right into 180 upon pi. So, it comes in the degree, where A is the log of the intensity I upon I naught. So, initial intensity upon the final intensity or intensity at the time t, that we can relate with the Beer-Lambert law. Epsilon C is the concentration, and L is the path length. So, epsilon is the molar extinction coefficient, L is the path length and C is the concentration. Also we can convert this electricity to the molar electricity by simply playing with its molecular weight of that particular protein, and this is a result of you can see this is a native albumin which is having a positive peak at 192. So, we can say positive means plus sign. So, for alpha helix we will have positive peak at 192 and we may have two negative peaks at 208 and 222. So, we are having a negative peaks, this is the positive peaks, we have one negative here for the 208 and one negative here for the 222. Now, if we are hitting this albumin at 50, 65 and 75, it means there is a change in its secondary structure, that we can analyze whether there is a formation of beta sheet or not. So, for beta sheet, this positive peak will shift to 195 and the negative peak will shift to 216 or 175. So, here we can see the intensity of the particularly this 208 is totally gone, also the 222 is shifted towards here this 216. This peak position is shifted towards here. So, depending on the peak position, we have various models to analyze directly the secondary structure of the adsorbed protein. So, here the advantage of the circular dichorism is we can directly analyze using the aqueous consent solution of the protein, we need not replace H2O with D2O. So, thank you, here I conclude. So, today we discussed if there is a protein surface interaction. So, we have to see what is the adsorb amount. So, adsorb amount we can analyze using that labeling method, colorimetric method or instrument methods like SPR, ellipsometry and QCM. Also, we have to analyze viscoelastic properties. So, if you can monitor dissipation energy, you can calculate or comment whether it is a rigid layer or the soft layer, and change in the secondary structure during the adsorption we can analyze using the FTIR or the circular dichorism. Thank you.